Hello guys, so welcome back to our second marathon series for soil science, and today in this series we are going to start with soil physics exclusively. So please join fast, and I'm your mentor and my name is Purbita and I'm currently pursuing my masters from the Division of Soil Science and Agricultural Chemistry in IRI New Delhi. So I welcome you, each and every one of you, to this session, and I would like a response in the chat box if my video is clear, if my audio is clear. So please guys respond in the chat box and then we can start. Very good morning, Shamik. Sorry, evening, not morning. Okay. So is my audio and video clear? Please drop a response in the chat box, guys, if my audio and video is clear. Okay. Welcome each and every one of you. So we will begin now with soil physics. So we had completed pedology in yesterday's lecture, and those of you who had not attended the previous marathon, I would request you, because pedology is one of the most important topics that is often repeated in JRF physical science. So please go and give it a watch. And if you do not understand the concept of pedology, then you can not move further, okay, because that is concerned with the genesis of the soil. Now here we are going to read about soil physics. So we know that there are different branches of soil science, right? Pedology, physics, chemistry, fertility, so biology. Here we will start with all the physical parameters that govern soil, okay? What is the physics behind it? So the first thing that comes to our mind is, what is soil made up of? Yes, good evening to each and every one of you. So the first thing that comes to our mind is, what is soil made up of? In the previous lecture in pedology, I'm really sorry for the interruption, guys. So we'll again resume from where we had just ended. So we'll Okay, fine. So we were seeing the different composition or the volumetric composition of our soil, and with that we had learned that 50% of our soil is composed of mineral matter. Okay, and within that mineral matter, that this 45%, it is very important, it is constituting all the soil separates. Now the first thing is your soil texture that you should know. So what is texture? It is the relative proportion or the amounts of the different primary separates that make up our soil. Now mind you, in this case, you will never include the non-soil particles that are greater than 2 mm in diameter. No, you will never include stone, gravels or all the other things. You are just only concerned with the sand, silt and the clay fraction. Now this sand and silt fraction, this is called as the skeleton of the soil. Like in your body, the bones, they make up your skeleton. Similarly, in the soil, the sand and silt particles, they together bring about the framework of the soil, and the clay is just like your muscle or the flesh. Okay, now also mind you that this sand and silt, these belong to the coarser fractions of our soil. When we will see the textural analysis, we will find that this belong to the coarser fractions of our soil, whereas the clay, it is a finer fraction of our soil, right? And the sand and silt, it does not contribute to any of the chemical properties, it will just contribute to the physical property. But the clay here is one of the most important things that has everything, that has charge, that has aggregation capacity, that has the capacity to hold the soil particles together. So that is why it is called as the flesh. Imagine you are walking with your skeleton only, with no muscle. So that is how important your clay is, okay, in the soil. Now we will classify the different soil separates, okay, accordingly. And we have actually two major systems of classification. One is International Society of Soil Science, and this was renamed from IUSS. Now who will tell me that this IUSS, what is the full form of IUSS, and when did the IUSS get converted into ISSS? Okay, so I want that in the chat box. Now, according to the International Society of Soil Science, we are classifying the separates into four major fractions. Two are for sand and the rest is for silt, and the final one is for clay. Now, in each and every classification, the clay will always be less than 0.002 millimeter in diameter. Now, students often make this mistake that suppose in one question you are given as radius, that identify the radius of your soil, but you have read all these values. So, you will go and tick the one with 2 in there, but you should not do that because this is diameter. And whenever we want to find out the radius, we will always have to divide it by 2. So, I haven't got the answer in the chat box that when did this IUSS get converted to ISSS. Okay. So, here you see that the ratio in between the particles is 10. It is 1:10 for each and every particle size. That means if we go from clay to silt, 10 times the particle will be bigger. And here the upper limit is 2. In each and every classification, you will see that the upper limit is 2. Now, in the next case, we are classifying the soil according to USDA classification. All this is very important. You should remember that which of the soil separates fall under which category. So, now here in case of USDA only, we have classified the sand into 5 major groups: very coarse, medium, fine and very fine. The clay is always less than 0.002 millimeter, but here there is the catch that the particle size increases twice as we go up. So, 2 times or 2.5 times, if you multiply that, you will get this value. Okay, so these two systems of classification you should read very, very thoroughly. Now, there is another system of classification, and that we can say that it is called as your British Standard System of Classification. British Standard System of Classification. So, here also your soil, it is the clay particle is less than 0.002 millimeter in diameter, but whenever we move to silt part, it will be 0.002 to 0.06. So, here each and every value will be in the order of 0.06. Then when we move to sand, it is 0.6 like that, or 0.006 like that. Okay, 0.06, sorry. So, in this British Standard System of Classification also, you can see that 10 times increase is there, but all the values will be concerned with 6. So, whenever you will have 6 in your option, just mind that it is the British Standard System of Classification. And here also, the sand, the coarse sand, it will not exceed 2 millimeter in diameter. So, it will always be in this range of 2 millimeter. Okay. So, the entire range of our soil separates is what? It is from 0.002 millimeter to 2 millimeter, and that is true for each and every system. But you can ask me that, ma'am, we have also other particles like that of stone, beds, gravel. So, where will we include them? They are also the part of soil, but they are not considered as soil separates or primary particles. Okay, we classify them in a different manner. Now, this is the classification of the non-soil particles in a different manner. You see that we have actually two different systems of classification. This one is for round particles, and this one is for flat particles. Okay. So, either your particles might be flat or it may be round. So, this round particle is gravel. Okay, gravel, cobble, stone, boulder, and you have to memorize the diameter of each and every particle. Okay. So, you see that it starts from around 2. Okay. But here in the new ISSS, it is given that there is another thing called pebble, and that pebble, it can occur in between 2 to 4 millimeter. Okay. The pebble is occurring in between 2 to 4 millimeter, and from 4 to 7.5 we have cobble. Fine. Now, for the flat shaped particles, the range of diameter is a bit higher, that is 0.2 to 15 centimeter, and then 15 to 380, 380 to 600, and greater than 600. So, I am telling the units in millimeter. Also keep that in mind, these are given in centimeter, but when you convert it into millimeter, you have to multiply it by 10. So, this is the overall classification of the non-soil fraction as well. So, let us quickly view what are the properties of these three primary fractions or the textural separates of your soil. The first one is sand. Okay. So, mind you that gravel and stone and all that non-soil particles, they have not much contribution to the mineral density, but all these three particles, they play immense role. So, the first one is sand. So, it is estimated by sieves. So, you generally take a sieve of 2 millimeter and then you sieve your soil out, and it is visible to naked eye. So, you can easily take one particle of sand and you can see it with your naked eye, and the shape will be roughly spherical. Okay. The shape will be roughly spherical. Now, another thing is that we have the silt fraction and we have the clay fraction. So, in that silt fraction, the silt fraction is not visible to our naked eye, but it will have some properties which is buttery, okay, or you can feel it with your hand, or flaky in nature, and that will be in between the sand and clay fraction. And it can also be seen through an ordinary microscope. It is determined by sedimentation. So, first we will see that whenever we do the textural analysis of our soil, the sand fraction actually, it is separated by sieving, but rest the silt plus clay fraction, it has to be separated by sedimentation. And this silt fraction actually is the basis for the soil crusting. So, that we will cover later. But these two particles, sand and silt, they do not contribute much to the chemical properties. The most important one is our clay fraction, and that is very, very fine. Okay. These are either platy or spherical, and it is highly sticky, highly plastic, and some clays, they might swell upon wetting or shrink upon drying. Okay. Fine. Now, we will come to the methods of mechanical exchange in our soil. Okay. We will come to the methods of mechanical analysis of our soil. So, the first one is, we have two methods. One is international pipette method and the other is hydrometer, Boyescosmic hydrometer method. So, can you guys just wait a bit? Guys, can you please drop a comment in the chat box if I am audible or visible? I had a bit of problem with seeing your chats. So, can you please drop a response so that we can know that you are here? Okay, thank you, Samik, for the reply. Now, so we were discussing about the different methods of mechanical analysis of our soil separates, and we have two most important methods. One is the international pipette method and the other is Boyescosmic hydrometer method. So, you see that the international pipette method is the most standard method for estimation, and because this is the standard method, it takes much time to complete this method. Whereas, the Boyescosmic hydrometer method, it is a rapid analysis, and that you can at one go measure the texture of different soil samples together. Okay. So, who can comment that what is the basis for this international pipette method and hydrometer method? I want the answer in the chat box. Okay, who can comment what is the basis for these two methods? So, for the international pipette method, it is actually based on the principle of sedimentation. Why? The sand, silt and clay particles, they have different textural sizes, right? The clay is very small, very fine, as I mentioned, less than 0.002 millimeter in diameter. So, because it is very fine, it will take very long time to settle down. So, if you throw a stone in a pool of water, then you will find that the stone has reached the bottom of the lake in a relatively shorter time. Okay, but if you throw a particle that has a lighter weight or less density, then you will find that it sediments at a much longer time compared to the stone, right? Here also, for the sand particles or the silt particles I am talking about, because the sand we do not measure with the help of sedimentation. So, the silt particles actually, because they are 10 times larger than that of the clay fraction, they will take little time to settle down. And based on this settling velocity, we can classify our particles and we can find out the texture of our soil. Fine? Okay. Anti-flicker karke. Okay, ma'am, there is a screen in the middle of your video. Okay, don't worry. So, then we have hydrometer method. So, for the principle of hydrometer method, it is actually based on a continuous decrease in density of the soil suspension. Now, is it fine? The video is clear? Okay. Now, in case of hydrometer method, there is a continuous decrease in density. So, when you keep your soil suspension for a longer time, you will see that the density will slowly decrease because there is sedimentation. The clay particles, they will settle down, the silt particles, they will settle down. So, these two principles very important, never forget. Now, initially, if we are not doing the laboratory analysis, then we can just classify the texture with feel method. And this was a question, this was a PYQ in the year 2025. That how can you feel that what is the texture of your soil, or how can you feel through the feel method, how can you identify what is the percentage of moisture in your soil. So, that was a PYQ, and feel method will give you a sense of feel. So, if your soil is not at all sticky, you will take the index finger and the thumb, and if it is not sticky, if it is coarser, not sticking to your hand, then it is sand. If you feel that it is not sticking to your fingers, then it is silt, but it is feeling like a bit buttery, then it is silt. And if it sticks to your fingers, that means it has very high adhesive properties, then it is clay. So, by field method, we can classify it in our field. Then in the laboratory method, all this mechanical analysis like international pipette and hydrometer will come. Now, in the field method, there are actually three processes of soil textural analysis. One is ball formation, and the other is ribbon formation, and the other is staining. So, what is ball formation? You will take a lump of soil and you will find that whether it can form a ball or not. And if it forms a ball, whether or not it retains its shape. Okay. So, that will indicate that your soil has very high cohesive properties. Cohesive properties means it prefers sticking to each other. Now, in case of ribbon formation, we actually do this to measure the plasticity of our soil. And here, we will see that whether or not the soil is forming a 15 centimeter long ribbon with a diameter of about 3.8 centimeters. So, it has to form a ribbon. Okay, 15 centimeter long, 3.8 centimeter in diameter, and that ribbon has to retain its shape. So, that will tell you that the soil is plastic enough. Okay, that means it has a significant percentage of clay. And in case of staining method, either the soil is staining your equipments or your hand. Okay, so that will indicate your soil has greater adhesive properties. Okay, so in these three different processes, you can feel your soil with the help of feel method. Now, I had already mentioned the mechanical analysis. So, when will you go for mechanical analysis? I told you that for the sand particles, we actually prefer it by sieving. Okay. Now, let me show you the diameter. You see that here, in case of your USDA classification system, the silt starts from 0.05 millimeter. And in the ISSS classification also, the silt is starting from 0.02 millimeter. So, we can assume that 0.02 and 0.05 are very similar to each other. Yes, 5 mesh. Okay, very good, Chaman. So, That's why, because we will take only the silt and the clay fraction in our soil, we will actually sieve it, or we will do the mechanical analysis for the particles that are 0.05 millimeter in diameter or less than that. Okay, so this is a very important criterion. Fine. Now moving ahead. Now, before mechanical analysis, you know that your soil is not like individual textural particles, right? It is completely in an aggregated form. There are several foreign particles, roots, clods, beds, etc. It forms a very complex structure. It is not isolated. So, for doing the textural analysis, we have to find out what is the soil texture. And in texture, I told you that we will measure the primary particles. So, for measuring the primary particles, we will have to separate them, okay, isolate them. Then you will have to go for textural analysis. So, for isolation, we have to see that what are the cementing agents. So, these cementing agents, they can either be organic matter or the different oxides of manganese, sesqui oxides, soluble salts, polyvalent cations, carbonates. They can form bridges. Okay, so they will form bridges like clay is there, then you have organic matter, then you can have a cation, then again organic matter clay. So in this way, it forms a very complex structure, and you need to separate that out. And whether or not your soil has cohesive properties. So if your soil has cohesive properties, it will stick to one another, right? So this cementing or floccuating agents, we call it as floccuation. I'll explain to you in details what is floccuation. We have to disperse the soil. Okay, we have to separate them out. So these are all the different dispersing agents that you should remember. So for separating the organic matter, we can use hydrogen peroxide. So we can either use a 30% concentration or a 6% concentration. So if you have long enough time, then you can use 6%. If you have a shorter time, then you can use 30%. Yes, it is just like colloids. Now also you have sodium hypochlorite solution, NaOCl. Okay. Then in case of sesqui oxides, you will separate it with oxalic acid, sodium sulfate, sodium citrate bicarbonate dithionate. So this is very important method. Generally, to remove the sesqui oxides, we use this sodium citrate bicarbonate dithionite treatment. Okay, please remember. Then for separating the soluble salts and the polyvalent cations, we will use sodium hexametaphosphate. And then there is another term which is called calgon. So who can tell me the composition of calgon? Who can tell me the composition of calgon? So sodium hexametaphosphate is there, and for cohesion or adhesion we can go for mechanical methods like boiling in water, shaking, titration, ultrasound vibration, etc. So who can tell me that what is the composition of calgon? I want the answer in the chat box. Now, so this is how you can actually estimate the textural classes of your soil. Now, after doing the hydrometer method or after doing the international pipette method, you will find, suppose sand is there and your sand is suppose coming 40%, okay. Then suppose your clay is there, it is coming 20%. Your silt is there and it is coming, this is 40%. So now you have to say that what is your soil textural class. So yes, very good. So the formula of calgon is actually, it is 40% sodium hexametaphosphate, you can say, and 10% sodium bicarbonate. So if you have 100 gram, then 40% will be made up of sodium hexametaphosphate and 10% will be made up of sodium hydroxide might also be there. Bicarbonate we can also use, or we can even use carbonate. So these three we can use, okay, for calgon. But the basic component is the sodium hexametaphosphate. Okay. Now what I was discussing is that after finding out the relative proportions of sand, silt and clay, you will have to assign a particular textural class to your soil, okay, a particular textural class. Now, we were talking about soil texture, but in the soil texture, we have suppose sand, okay, we have silt and we have clay. These are the primary particles, but your soil is not found as such. So, we have to assign them to a particular textural class, okay, to a particular textural class, and that class will determine that what is the dominant fraction in your soil, whether or not it is sandy, whether or not it is loam. Okay, it will be silty loam. So, guys are already answering. Yeah. Okay. So, let's see. So, in case of our textural class, we have to assign that what is the dominant particle present, right? So, in case of sand, wherever your textural class will be there, always remember that whatever is the dominant particle, it will end like that. Wherever is your dominant particle, the suffix will be like that. And now, suppose if I have a sandy soil and if I have some fractions of loam dominated over here, then I can write that it is loamy sand. Okay, loamy sand. Then silt is not found as such. Silt is not found as such. It is not a textural class. So, instead the textural class is called as loam. So, silt is a primary separate, but it is not a textural class. The textural class is given by loam. Okay, it is given by Milton and Whitney. Okay, fine. The textural class is given by Milton and Whitney, but again another question I'll throw at you, just wait for a second. So, the dominant fraction will be loam, and in that loam always remember that the sand, silt and clay, they will not be present in equal proportion. So, many do this mistake, they think that okay, it is loam, so there might be 33.33% sand, 33.33% clay and 33.33% silt, but it is not that. In case of loam, the particles will be arranged in such a way that the properties, they will be similar or they will be in between sand and clay, but the relative proportions will never be equal, and that is a direct line from new IEEE. They have clearly mentioned that it will not contain exact proportions or same proportions of the primary particles, but their relative, you can say properties, they will be in between sand and clay. Fine. Okay, why means? See, because soil is a dynamic system. You cannot expect your soil to have the same fractions of these primary separates, and again, you cannot have a fixed fraction for loam. You will see that you have sandy loam, you have silty clay loam, you have silty loam. So, we have several classes of loam, right? And to qualify for loam, you cannot have that criteria that it should be 33.33% only. So, you have to assign loam to a range, and we saw that in our soil generally that range is not present. Okay, that specific or discrete value is not present. It is always present in the range. So, that is why they classified that in case of loam, the properties will be similar, but the proportions of sand, silt and clay may vary. Like the example I wrote, you see here it is neither 33.33%. Okay, it is not that, but this will fall under the loam as the textural class. Now, got it? Okay. So, in this way, we will have several textural classes, and we have 12 textural classes in total. So, after getting the different values of sand, silt and clay, you have to go to a thing called the soil textural triangle. So, this is the soil textural triangle. Okay, so this is the soil textural triangle, and you have to go to this textural triangle and find out that what is the percentages of these aggregates. Now, who will tell me that what is in these three sides? Please comment in the chat box what are the three major proportions in the three sides of a triangle. Okay, I want the answer in the chat box. Now, someone also told me that this textural class was given by Milton and Whitney. Fine. But who gave the textural triangle? Textural triangle is given by whom? That is also a question. Textural triangle is given by whom? Okay, so sand, silt and clay, so we all know. But where it is present? Sand, silt and clay, where it is present? Okay, so in the right side. So in this side, we will have silt. Fine. Then where is clay present? Lower side, it is sand. Very good. And here we will have the clay. Okay. And because the loam has more or less similar properties, here will be your loam. And on the top, we will have clay. and all these different fractions we will have sand. Okay, we will have sand. And suppose you have 3 different values, so that 3 different values you will put or plot in your triangle. So I have what? I have 40% sand, 20% clay and 40% silt. So suppose the sand 40%, it will fall somewhere over here. Okay, then for the 20% clay, suppose I have 20% clay, and then suppose I have 40% silt. So it will fall somewhere over here, and whatever textural class is present in your textural triangle, that soil will simply belong to that textural class. Okay, loam is at the center. Yes, loam is at the center. So this is how you are then going to find out the textural class of your soil. So what did we learn from it? We learned that the primary separates are not present as discrete entities. So discrete entities are not there, and the soil will always form a complex. Okay, and that complex is called a textural class. And different soils, they will be assigned to each and every textural class. So how can we measure that what are the different textural classes? Always remember that for sand, it is actually, if it contains greater than 80%, then it will belong to sand as the textural class. Okay. Then, and it has to qualify for less than 12% of clay. Less than 12% of clay and greater than 75% of sand. So that will belong to silt. Silt fraction, silt size fractions. Okay. Then for the clay, if you want your class to be a clay, then for that you have to have a minimum of greater than 40% of clay. 35 to 40% of clay must be there. But there is another catch. So if suppose I have taken a particular textural class to be silty clay, suppose if my textural class is silty clay, then, or okay, let me just clarify one thing. So if suppose I have a suffix that is silt and I am having a prefix that is clay. Just wait a second. Suppose if I have written this to be the textural class, the clay is the suffix and the silt is the prefix. Silt is the prefix. So this first term that will come, where you will add y, it is also called as a modifier class. Okay, this is called as a modifier class. That means the next dominant fraction that will influence the texture of your soil. If 40%, it will be clay, yes. So that is called as a modifier class, that the prefix that we add. So in case of clay, we know that it is greater than 40%, no issues, but then silt is the next dominant material. So in case of a silty clay soil, the proportion of silt, it will be greater than that of clay. This is also a line taken directly from the new IEEE. So if your textural class is silty clay, then the silt percentage, it will be more than that of clay, because clay, to qualify for clay textural class, you only need greater than 40%. Okay. So these small things along with the percentages you have to remember, and it would be very beneficial if you can also remember that what are the different textural classes that fall under sand, loam and clay. Okay. What are the different classes that fall under sand, loam and clay? And we have altogether 12 textural classes. So you should learn that what are the classes, how many classes are qualifying under sand, loam and clay. So that you must remember. Okay. So texture is over. Now the next best thing after texture is your structure. So I told you that they are not present as discrete particles, so they have to form some kind of structure, right? So texture is the proportion, but structure, it is the arrangement. So it is the relative arrangement. Okay. So structure is the relative arrangement. Let's just see one thing. Okay. Okay. So you see that first is your soil structure. It will be the relative arrangement of different particles, and that particles will include your sand, silt and clay. Fine. That particles will be your 3 primary separates, that is sand, silt and clay. Now another thing is there, you will often find in the soil that there are several particles that are round in shape, okay, forming an aggregate. So all these things, they will together combine to form one aggregate. So what is an aggregate? Aggregate is when the three particles, they come together and they are cemented by a particular agent. So this aggregation in your soil is equal to flocculation plus coagulation. Sorry, flocculation plus cementation. So that is why aggregation is also called as flocculation plus. Flocculation plus. Why is it plus? Because it also involves cementation. Sand, loamy sand, sandy loam, silt loam, okay, silt, sandy clay, okay, very good, very good. Vipin, okay, Vipin, sorry, very good. So he has written all the different textural classes in the chat box, very good. Now we were explaining about the aggregation, flocculation and cementation. So what is called flocculation? Please repeat, which one? Okay, so see, for the aggregation, what will happen? It is actually flocculation plus cementation. So how will that take place? You have different aggregates. Suppose this is sand, okay, so there are different aggregates and they are in a dispersed condition, okay, they are present scattered randomly. I am repeating, I am talking about flocculation. So they are scattered randomly in your soil, and when these particles, they will come together. When the particles are coming together, they are getting floccuated. That means they are coming together. Now they are in proximity, they are close to one another. So this process of getting close is called flocculation, okay. So you can imagine it in this way, that you are building a friendship with someone. Previously you did not know each other, but slowly you are getting to know each other and you are coming closer day by day. So that is called flocculation. Now after coming closer, you are going to form a bond. So that formation of bond is very important. So whenever the floccuated aggregates, they will get cemented together, okay, a bond is formed in between this floccuated particle so that it does not get separated. So this process is called cementation. And now you are a pair. So that is what is called as your aggregation. Fine? Got it? The difference between flocculation, cementation and 40 plus questions from soil physics, very important topic. Actually, we had covered our most expected series, okay, just the previous month, at the end of the previous month, and you can go and watch the videos, okay, for the 40 plus most important questions of soil physics. And if you want to practice your soil physics, then you can always subscribe to our master course or the test series. It is also available. You can solve the PYQs and mock test bundles. You will get all the questions aligned over there. Okay, got it? Now just concentrate on the lecture. So flocculation plus cementation will build you aggregation, and these are the cementing agents that I just mentioned that you need to disperse. So the opposite of flocculation, it is called as your dispersion. Dispersion means what? Already floccuated particles were there and then breakup happened. So that is called as dispersion. So when your particles, they were floccuated and they are getting separated from each other, scattered from each other. So that is called as your dispersion. Clear? The idea of flocculation, cementation and aggregation. So always remember that for aggregation to happen, you need cementation. So it is called flocculation plus. Clear? Now, as I was mentioning that the soil structure is there and it is the relative arrangement. So, all these aggregates, they are also present in your soil, and based on that, your aggregates will be classified into several factors. If you have natural aggregates, then it is called PEDs. If you have artificial aggregates formed during tillage, then it is called clods. Okay. If you have broken PEDs, then it is called fragment. Then it is called fragment. And if you have other depositions of either sesqui oxides or calcium carbonates, then it forms concretions or nodules. Clear? So these are the different arrangements of the different secondary structures that might be present in your soil. Okay. Now we will come to a very important part, that is the different types of soil structure. So always remember that the soil structure, it is evaluated by three ways. One is the grade, then we have class, and then we have type. So the grade will actually give you whether or not your soil is weak, moderate, strong or structureless. The class will tell you the relative ranges of the particles, sizes or dimensions, and the type will tell you what is the type of structure present. So first one, very important, platy, that means it is plate-like. Plate-like, you can imagine. So if the plate-like structure is thin, then it is called laminar. Okay, laminar structure, if it is very thin, the diameter is very thin there. Okay, it is called as a laminar structure. Now, always, okay, another thing you have to remember that this platy kind of structure is actually formed in E horizon of forest soils. E horizon of forest soils or grasslands. So E horizon is a surface horizon. So it is going to form in the surface horizon of forest soil or grassland. Very important. Okay, this often came. Ma'am, in plate, if it is horizontal and prism, it is vertical. Yes. So if the horizontal axis, this one, it is elongated, then it is plate. If the vertical axis is elongated, then we come to our next structure, which is prism shaped. Okay. So in that prism shaped, always remember this prism and block like structures, they are always found in subsurface horizon. Never in the surface horizon. Subsurface means B horizon. Okay. Subsurface means B horizon. So plate is structure surface horizon, prism and block subsurface horizon. So this prism block, I told you that it is vertical. Now if suppose your soil, it is very salty, it is saline. In case of arid and semi-arid region, in case of arid and semi-arid regions where precipitation is very less, evapotranspiration is very high, then this upper plate-like things, they will form columnar structure. They will become rounded and it will form columnar structure. Clear? Now the next one is block-like structure. So in this block-like structure, this line, it is very important. All the three dimensions of beds are about the same size. And if your beds, they are angular, then it is called angular blocky. If the edges are rounded, then it is called subangular blocky. Edges are rounded. Okay. So this is also found in the subsurface soil, that is in B horizon. So never forget that. Okay, B horizon. Same in arid and semi-arid regions only. Then the fourth portion is spheroidal. So this type of structure is most important for agricultural point of view. Why? Here all the axes are developed equally with the same length. So do not confuse between the block. In block we have three dimensions and in spheroidal we have equally developed axes. Columnar in sodic soil. Yes, columnar, saline, alkaline, sodic soil, you can find that. Even saline sodic soils as well. Now, in case of spheroidal structure, that is also found in your surface horizon, and there are two types of spheroidal structure. One is granular and the other is crumby. And within that, the crumby one, it is more porous. Okay, it is more porous and it is more important for cultivation purpose. So, what is the best structure for cultivation? It is crumby, not granular. Clear? Clear, each and every one of you? Okay. Now, next. Now, as I mentioned that we will have some classes of soil structure. So, what are the classes? Either it can be very fine or very thin, that is less than 1 millimeter. So, it is platy. Then you can have fine 1 to 2 millimeter. Then you can have medium, that is 2 to 5 millimeter, and coarse and very coarse is greater than 5 millimeter. So, based on the dimensions or based on the different types, you have an entire chart given in old ISSS or new ISSS, whichever standard book of soil science you want to follow. So, you can memorize the dimensions of each and every type at least you have to memorize what is the maximum limit and the minimum limit. Okay, so that one you should memorize for the different classes. Okay, so it is dependent on what you see, equivalent diameters of beds or aggregates. So whenever we are talking about soil structure, we are not only concentrated with the individual soil separates, but now we are focusing on the aggregation. What is the aggregation? Now the third point is grade. So whenever I told you that we evaluate the structure, we will begin with grade. If I want to evaluate your performance in JRF physical science, first of all, I have to identify whether you are sitting for physical science or not. If you want to go for plant science, why would I evaluate you, right? So for the grade, I have to see that whether or not the soil is structureless. If it is structureless, then the class and type will not come. So in the grade, we will see whether your soil is structureless or whether or not it is structured. Clear? So what is structureless soil? Structureless soil is, suppose you are taking a lump of soil and you are just allowing it to fall under gravity, and you see that whenever the beds are broken, okay, the individual or isolated particles you can find there. That means they are not in an aggregated position, number one, or number two, it might happen that they are in a massive form. So whenever we want to study our structureless soil, either they can be massive or cohesive, okay, or they can be single grain. So for the single grain structure, we have sand because individual particles are there, and for the massive or cohesive structure, you will have puddled soils. In some books, it is also mentioned that there is a third type of structureless soil, which is highly weathered bedrock, that is saprolite. Okay, that can also fall under structureless soil. Grade, distinctive and durability, yes, class is related to size and type for the shape and arrangement, rightly said. So these are the three classes of your structureless soil that you can find. Now coming to the structured soil. So in case of structured soil, you can have weak, moderate or strong. Weak means whenever you throw a lump of soil, it will not dissociate into distinct fractions. Okay. So these are non-durable and they are poorly formed. Moderate means okay, somewhat distinct and somewhat non-distinct, and strong means they are very, very strongly formed and they are durable. Clear? Now, the next thing that comes under structure is, okay, before that let me tell you that we can evaluate our soil structure. Okay, so we are writing here evaluation of our soil structure, and that evaluation of our soil structure we can either do with the help of direct methods or indirect methods. So whenever we go to direct methods, we can have what? We can have petrographic microscope. So, you are directly taking your soil, you are placing it under a petrographic. Petrographic means it is related to rock arrangement and formation. So, you are directly keeping it under microscope and you are analyzing the class, size, type of structure so that you can do directly. But if you want to do it in an indirect method, then you have to bring about several coefficients. The first one is mean weight diameter. Second one is geometric mean weight diameter that you can find out. And then we can have change in mean weight diameter, that is CMWD, that you can also follow. So whenever it is mean weight diameter means, suppose you have a soil, suppose you have Xi, that is the percentage of different aggregates or proportions of aggregates having a weight of Wi. So in case of mean weight diameter, you are just going to sum them all up. Summation of Xi into Wi. Whenever you have geometric mean weight diameter, you are going to take logarithmic scale of that. And whenever you have the change in mean weight diameter, that is used to measure the change in case of water stable aggregates and poor aggregates, okay, and mechanically separated aggregates. So technically it is telling you that what is the percentage of aggregation. And the less the change, if the lower the mean change in mean weight diameter is, the better is your soil structure. So this is how you can evaluate the soil structure. Now, another methods might come where you can also evaluate the aggregate stability of your soil. Aggregate stability you can measure for your soil, or you can also go for indirect methods of structural analysis with the help of structural coefficients. Okay, then dispersion coefficient is also there, then stability index is there, then water drop method is there. So through all this you can also evaluate the structure of your soil, and direct and indirect method given by Biswas and Mukherjee. Yes, and that is why it is present in T.D. Biswas and Mukherjee book. Okay, so you can always refer to T.D. Biswas and Mukherjee for that. I am also writing it down here, and it will be very helpful for you if you can remember the formulas as well. Okay, formulas of all this indirect method of analysis you can remember. Often questions, direct questions like numericals doesn't come, but they can give you statement wise questions that this is that or state true or false like that. So, it will be better if you remember those. Okay. Now, we have completed the soil structure. Now, there one thing I am leaving, it is the importance of soil structure and texture. It is very easy. I think you guys are smart enough to know that what is the importance of structure and texture, how it will affect your plant growth. If your structure is good, okay, then always there will be better plant growth. Higher the water drop method, more stable the soil structure. Yes, because in case of water drop method, we actually measure that how many drops of water, okay, from 4.7 millimeter height we will be dropping water, and we are measuring that how many drops of water are required to break a soil structure. So, if more number of drops are required, obviously the stability of the soil will be more. Now, the importance of soil structure and texture, I think you guys are smart enough to know. Now, we will move into the next important part of this topic, which is soil consistency. Okay. So, what is consistency? It is the resistance of a soil to deformation or rupture under applied pressure. And those of you who had seen my class, they are marathon for CVT PG, you guys know that I stress on two definitions. One is soil consistency and the other one is soil strength. So, the definitions are very similar to one another. But for consistency, it is the resistant to deformation under applied pressure. So, you are applying the pressure and you are seeing whether or not that soil can retain the pressure or retain the newly found structure. So, that will come under consistency. That means suppose you have a lump of soil and you have applied some pressure so that it can form a ball, and with your consistency you will see that whether or not it can retain the structure after the applied pressure is there. So, the consistency will also deal with the retainment of the structure or the deformation. So, the deformation term comes. But whenever I will be discussing soil strength, you will see that the soil strength is when you are resisting the deformation. That means I will say that a soil has more strength if it does not alter at all. Clear? How many numerical questions in physical science, any guesses? You can take from 3 to 4. 3 to 4, or in some papers it is 2 to 3 or 3 to 4, and if you are unlucky then 4 to 5 might come from pH also, it might come, but mostly 2 to 3, 3 to 4, that's it. Okay, that's my best guess. Okay, now coming to the soil consistency, it is a manifestation of physical forces of adhesion and cohesion acting within a soil at various moisture contents. I'll explain it just a second. So, as I was saying previously that whenever you will find out what is consistency, consistency in any case it is the interplay, of the different forces that act on a body. Okay, and with consistency another term called rheology it comes into play, and this rheology is actually the study of fluids, how they flow. Okay, flow of fluids. while analyzing the volumetric composition of our soil, we saw that only 50% is solid matter, but the rest 50% is made up of air and water. So, this soil is nothing but an interplay of air, water, solid. So, that air, water, their dynamic properties, right? They will always alter. Okay. Okay, one thing I forgot to mention is that the soil texture, please comment whether or not it is a static or a dynamic. What kind of a property is it? Static or dynamic? Please comment the soil texture. Now, for the consistency, actually two forces will come into play: cohesion, adhesion. And in some cases, another thing might come, that is capillary action. So, that is related with moisture. So, whenever I want to define that whether or not our soil is consistent, we have to take into account these three forces. Cohesion means similar kind of particles, the force that happens in between similar kind of particles. Adhesion means dissimilar kind of particles. Suppose I am taking soil and I am taking water, that is adhesion. I am taking water, water or soil, soil, that is cohesion. And what is capillary action? Capillary action, it is the phenomenon in which a soil or water in a soil, it will rise through a very, very narrow pore. So, it is the rising action of water, and that is due to surface tension. Okay, due to the surface tension of whatever water or moisture is present in the soil. No, Soumik, you are wrong. The texture is a static property. That's why I asked the question. Why? Because it is mineral matter. You cannot change the texture, you cannot alter, you cannot make a sandy soil entirely clay, or it would have alleviated more than half of our problems, right? Why are we discussing so much about changing the soil structure or making it good? Because we cannot alter the texture. We can only do a few modifications, like if we add sand to clay, a very sticky soil, suppose we are adding sand and it is called marling, okay, or we can even break the cloths and alter the texture through repeated manuring and tillage we can do, but we cannot change the soil structure as a whole, sorry, soil texture as a whole. So, these are the two ways by which we can only alter it, but we cannot change it, okay. Both cohesion and adhesion forces are responsible in both consistency and capillary rise. Yes, fine, Vipin. Now, you see that what I was talking about is that these are the three forces that are very, very important for proper soil consistency. Now, whenever I am talking about consistency, one thing must be very clear, that it is always associated with a percentage of moisture. Suppose we have two soils, okay, one is two clay soils, okay, you have in your hand, but one has 80% moisture and the other has 10% moisture. So, the 80% one, it will be more sticky, more viscous, right? But the 10% one, it won't. So, all the other conditions are constant, but the moisture percentage is changing, and in that case, you will find that this soil consistency is very, very important when we relate it to moisture. Okay, so we directly relate our soil consistency to moisture, and this is more due to cohesion. So, if the question or MCQ comes like, what is the main force responsible for consistency? It is cohesion, because cohesion will be in between soil. If your soil sticks to any foreign object, then your soil will not be that consistent. Consistency means what? You are maintaining a continuum. You are consistent in your preparation means you are reading every day. Okay, you are maintaining your preparation. So, if your soil is consistent, that means it will hold itself together. If it is not consistent, that means what? It will have more adhesive forces to it, it will stick to any other foreign object. So, that is why it is directly responsible due to cohesion. Now, according to your wetness also, the soil consistency will change. It is hard, soft, plastic, sticky and viscous. Hard, soft, plastic, sticky and viscous. So, these are the different percentages of moisture. So, whenever we go from here to here, the moisture percentage will increase. And always remember, your dry soil is more consistent than a moist soil, and it is again more consistent than a wet soil. Okay. And in case of puddled soils, they will be very compact, they will be highly cohesive. So, they will be much more consistent. Now, this is for moisture percentage, dry, moist and wet. So, dry will be more consistent than moist and then wet. Okay. So, these are all the limits of wetness or consistency that you can find, and this is directly associated with another term which is called PF. Now, what is PF? PF is the negative logarithm of height of water column in centimeter. In centimeter. So, whenever we have, and this term was given by Schofield, pH was given by Sorensen, Sorensen, PF given by Schofield, and PE was given by Sillen. Okay, these three terms don't forget. Now, you see that for the hard will always have a higher PF, that is around 4.5. For the soft, this is also friable, ideal consistency for tillage 2.8 to 4.5. For the plastic 0.5 to 2.8. For the sticky or viscous, it is around less than 0.5, and for the viscous, it is almost 0. So, these are the different PF limits that govern the soil consistency. You have to memorize this. This is very important. Now, what is soil plasticity? So, next to consistency, we have plasticity. So, plasticity is where it can be deformed into any shape, and it will maintain its shape even after the pressure is removed. So, you are deforming your soil and then the soil is retaining the shape. So, that means it will be plastic. So, if it has more than 15% clay, then it is plastic. Then your soil consistency, you see that it is optimum in the soft or friable range, and it is also optimum for puddling, and soil moisture content at which the soil ceases to stick to any other object, it is called sticky point. So, the limit at which it fails to stick. And here, regarding the soil consistency, actually there was a scientist whose name was Atterberg, and he gave the different limits of soil consistency: plastic, sticky, viscous, upper plastic limit, lower plastic limit. So, he gave the different soil consistency indices. If puddle soil of iron and white is less for wet, because wet soil is more compact than dry. See, I told you that it will depend directly on which property? Cohesion. Now, you tell me that a puddle soil, it is cohesive or not? Puddle soil, it is cohesive or not? Whenever you have soil, suppose you have the soil particles here, and you have loads of water in between. Loads of water in between. So, if water is there, then what will happen? Then adhesion forces will be more than cohesion, right? This is for wet soil. But in case of a dry soil, there is no water, so no chance of adhesion is there. So, it is cohesive. Now, in case of a puddle soil, you have to always remember that it is not directly dependent on the wetness. You are breaking the soil into so much finer fractions that it will be an entire lump. So, it will obviously be much more cohesive, right? So, it will be obviously be much more cohesive, and that is why we mentioned, right, that it is a kind of structureless soil. We also called it as massive or cohesive. So, that is why in case of puddle soil, the consistency is more. But whenever we talk about moisture percentages, whenever moisture is present in between the soil particles, that will reduce your cohesion. Now, clear? Yeah, good. Now, this Atterberg scientist, he gave different limits, and some of the important points that you have to remember is that the difference in between upper plastic limit and the lower plastic limit is called plasticity index. Okay, and it will help you to judge that whether or not your soil is plastic. So, this upper plastic limit, it is measured with the help of Casagrande's apparatus. Okay, it is also called liquid limit. It is also called liquid limit and measured with the help of Casagrande's apparatus. Now, another thing I wanted to clarify is that whenever we are talking about Atterberg's limits and whenever we are talking about all these consistency values, there will come a particular moisture content where your compaction It will be highest. Okay. So, that particular moisture content where the soil compaction is highest, it is called Proctor moisture content. Proctor moisture content. So, we will come to that later on. It is called Proctor moisture content. So, what you need to learn? You need to know about the different Atterberg limits. You need to know about the different PFs related to consistency and plasticity. And another thing you need to know is the coefficient of linear extensibility, that is COL. So, you need to know COL value. So, what is COL? Let me just write it down. Okay. So, you need to know what is COL. The COL is coefficient of linear extensibility. So, can anyone write the formula for COL? Can anyone write the formula for COL? And we have for vertisols and for Montmorillonite type of clay, the different limits of coefficient of linear extensibility. So, it is actually moist by dry minus 1. Length of moist soil by length of dry soil minus 1. Similarly, upper plastic limit, liquid limit, yes, and lower plastic limit, it is not a shrinkage limit, but you can just call that it is plastic limit or lower plastic limit. Okay. Now, this is length of moist soil divided by length of dry soil minus 1, or you can write it in terms of bulk density also, to the power 1 by 3 minus 1, anything you want. So, this is the coefficient of linear extensibility, and the values for vertisols and Montmorillonite, please do remember. So, for the vertisols of the cracking clay soil, it is generally greater than 0.03, and for Montmorillonite type of clay, it is greater than 0.09. Yes. Okay, into 100 also you can do, no worries. But you have to subtract this from, yes. So, into 100 you can find it in percentage, or if you do not want to find it in percentage, you can also keep it in fraction forms, no matter. Now, we come to, okay, so these are the evaluations of different soil structural methods that I had already explained with the help of board work, but you can always go through it. Okay. So, then change in mean weight diameter. Now, here is the management of soil structure. Now, why I brought this slide after the plasticity and cohesion? Because in order to understand the soil structure, you also need to understand the aggregate formation. And now, when I am going to talk about how you can manage the soil structure, you will find the use of different soil conditioners. So, what are soil conditioners? That will hold your structure together. Now, tell me, what is the charge of clay? Clay here, it is positive charged or negative charged? Clay fraction of your soil, it is positively charged or negatively charged? Ma'am, are PYQs? Obviously, Vipin. PYQs, they are very, very important, as sir rightly mentioned. Yesterday also somebody asked and sir said that if, as it is, PYQ is repeated. So, at least you should have 5 to 6 years or even more PYQs, and you should be very, very thorough with them. Clay is negative charged. Yes, very good. So, because the clay is negatively charged, whenever you want your structure to form, this is negative charged clay, this is another negative charged clay. So, to bring them together, you need what? An opposite charge. So, that opposite charge is a positive charge, and that positive charge will be brought about by polycationic conditioners. Polycationic means that they will be cationic in nature, so that will bind two clays together. So, these polycationic conditioners, they do what? They will form a bridge. They can form a bridge between clay and organic polymer, or even clay. So, organic matter, we know that in case of organic matter also, you have different groups like carboxylic, COO minus, or phenolic groups. So, they can also bind that with the negative charge of the clay. Okay, this polycationic conditioners. So, their main role will be to act as a bridge in between the two negatively charged particles. Then the polyanions. So, polyanions will do nothing but whatever structure is formed. Suppose if you have already an aggregate. Okay. The polyanionic conditioners, they will just coat the aggregate. So, they will form a coating over the aggregate, and they will help stabilizing the aggregate. They will not help in bridging. Only one, that is polycationic one, will help in bridging, but polyanionic one, they will just stabilize the aggregate. And the last one is your non-ionic. So, non-ionic, Very, very important, polyvinyl alcohol. Do remember the examples, okay. So, the non-ionic one also, it will help in aggregate stabilization. Only the cationic one will help in aggregate formation, but the rest two will help in stabilization. So, these are the methods. Either you can use soil conditioners artificially, or you can go for more natural methods, for example, organic manuring, green manuring, etc., etc. Now, just a second. Yeah. So, now we will talk about, okay, now specific value, okay. So, one thing is that I wanted to say that there are three different forms in which your soil or consistent forces might act. One is compaction, and the other is compression, and the other is consolidation. So, who can tell me what this means? Whenever you have compaction, there will be a decrease in volume, your volume will decrease and your bulk density will increase. You are compacting your soil, volume decreases, bulk density increases. Whenever you are undergoing compression, only there will be the decrease in volume, but bulk density will not change. And in case of consolidation, you will change it to such a way that you are expulsion of water from the pores. So, suppose you are compacting your soil and one time it might come that you have reached the level where the water is being expelled out from your pores. Consolidation, if only, elimination of water is there. So, Ronak sir is also answering. So, you all guys welcome Ronak sir. So, he is also one of our mentors. Okay, who will be also conducting the marathon series. So, he is also answering in the chat box. Now, these are the three processes by which consistent force might act in your soil. And as I mentioned that this proctor moisture content is the one where your soil will have maximum bulk density at a particular moisture. So, whenever we talk about bulk density, we always have to bring about the moisture content. Now, why? That we will learn in case of mass volume relationships. Okay. So, mass volume relationship means what? Now, you have this much percentage of air, this much percentage of water, and then you will have to find out that what is the relationship in between these, right? Now, first is density. So, within density, we have two things. One is particle density. This is also called is your true density. And in case of particle density, it is just the ratio of the soil solids to the volume of soil. So, normally for the formula of density, we know that it is m by v. But whenever we have particle density, we will only take the soil solid fractions, okay, mass of soil solid divided by the volume of soil solid. We will not take into account the pores. And another important thing is that the particle density of normal soil, it will always range from 2.6 to 2.7 gram per centimeter cube. This is because quartz is the most dominant mineral in our soil, and the quartz has a density that is very similar to this, around 2.85. So, that is why the particle density assumes a value that is very much similar to quartz. Okay. Now, it might change if organic matter content is much more. It will lower the particle density and it is measured with the help of pygnometer. That only you have to remember. Second most important thing, very important from agricultural point of view, is our bulk density. So, bulk density is whenever we will have the bulk density, we will consider the mass of soil solids, but we will consider the entire volume of your soil. It is Vt. So, because Vt, again, this total volume of our soil, it is much greater than the volume of soil solid. Why? Because the total volume will include air plus water plus solid. So, it is much greater than the soil solid. This denominator term increases. So, bulk density will always be less than particle density. Not very less, but it will be less than particle density. And the limit for bulk density is, in case of coarse textured soil it is high, and in case of fine textured soil it is low. Yeah, PD, BD. Now, you see that why? In case of coarse textured soil, mostly sand is the dominant fraction in case of coarse textured soil. So, in case of that, the total volume of sand, if you consider the entire volume of sand, it has very low water holding capacity, okay, very low porosity, okay, very low porosity. So that will decrease the total volume. Also, the mass of sand, it is much higher than that of clay. That is going to increase the numerator part. So that is why for coarse textured soil, your bulk density is greater than that of fine textured soil. Clear? Another thing is that we can divide the bulk density into two parts. One is a wet bulk density and the other is dry bulk density. So whenever we calculate the wet bulk density, we will take the mass of the soil plus the mass of the water divided by the total volume. But whenever we calculate the dry one, it will be only the mass of soil divided by the total volume. And here, if you increase the moisture content with increase in wetness, the bulk density will decrease because the total volume increases. So these are some of the points that you have to keep in mind. Okay. Now, yeah, so for compacted soil, it is always greater, that is 2. For organic matter, it is 0.5 gram per cc. For compacted soil, I am writing it over here. It is 2 gram per cc. Now, another numerical comes, that is what is the weight of 1 hectare farrow slice. Okay. So that also I have to do. So for the weight of 1 hectare farrow slice, 1 hectare means 10,000 meters square. Right, that you guys all know, 1 hectare means 10,000 meters square, and here we will take the average BD to be around 1.5 or 1.33, whatever you are comfortable with. So if we go with 1.33, then the value will be a bit lower. If we go with 1.5, then the value will be a bit higher. So, and also the depth. So whenever you are talking about plow layer, the depth will always be this V-shaped portion that has been cut by the plow layer, which is nothing but 6 inches or 15 centimeters. So you are going to do what? To find out the weight, you will multiply 1 hectare with the bulk density with that of the depth, and then you will get the weight of the soil in kgs per hectare. Clear? Ma'am, coarse and fine wala repeat please. See, in case of coarse textured soil, ma'am, please revise soil, air and temperature very nicely. Okay, don't worry, soil, air and temperature will also bring. Now, you see that in case of coarse textured soil, what I was talking about, yeah, in case of coarse textured soils, what I just mentioned, let me show you that. In case of coarse textured soil, the sand is there, right? So the water holding capacity of sand is less, the porosity is also less. One thing. So the total volume of a sand, if you take the volume of a sand, it will always be less than that of clay. Porosity is also less because we are considering the total volume. So this factor, that is the denominator factor, it is already decreasing, and the mass of sand, it is also greater than that of clay. So the numerator increases, denominator decreases. That means the bulk density will increase. Fine, got it? Did you get it? Okay, Soumik, did you get it? Yeah. So this is how we can calculate the weight of 1 hectare of farrow slice. Clear, everybody? Okay. Now coming to third important topic, that is specific volume of soil. So it is just 1 by bulk density. You are going to invert the bulk density, and so it will be less for coarse textured soil and it will be more for fine textured soil. And this line comes often in the exam, that what is the specific volume of a soil? It is the index of compactness or looseness of the soil aggregates. Clear? Index of compactness or looseness. Then we have porosity. So porosity is the ratio of total pore space to the total volume of a soil. So suppose pore space is Vf divided by Vt, and that Vf will include the air and water. So we can also calculate porosity by this particular equation, that is 1 minus Bd by Pd into 100. So that can give us the percentage porosity. and obviously for clay size fraction the porosity will be more. Ma'am, okay, means coarse, yeah, coarse means sand, C-O-A-R-S-E, it will be A-R-S-E, coarse, okay. Okay, just a second, just a second. Now, so this is another way by which we can classify the porosity, or we can find out the porosity of our soil. So, with porosity comes another term, that is pore spaces. So, if your soil has a pore space of greater than 0.06 millimeter, then it is macro. If it is less than 0.06 millimeter, then it is micro. There can be other classifications like cryptopores, ultramicropores, blah blah blah. So, you can all refer to the new ISSS for that. But in some books it is mentioned that the limit is 0.08 millimeter. So, whatever is there in the option you can tick it. Okay. Now, the fifth most important thing is your void ratio. So, void ratio means whatever is your volume of void divided by the total volume of the soil solid. So, it is Vf by Vs. Here we are considering solid, and in case of porosity we had considered the total volume of soil, and it is more important in agricultural point of view, and it varies from 0.3 to 2, 0.3 to 2. Now, this is the water content and the soil wetness. So, we will have gravimetric water content or mass wetness of our soil. So, whenever we are calculating the mass wetness, that means we will calculate the mass of water divided by the mass of soil solid, and whenever we are calculating the volumetric water content, it will be the volume of water divided by the volume of the soil solid. And the relationship in between water gravimetric and volumetric water content is gravimetric water content into bulk density is equal to volumetric water content. So, how did it come? Suppose this is gravimetric water content, this is theta m we are writing, okay, and this is volumetric water content, volume of water divided by the volume of the, okay, this is not soil solid, this will be total soil, okay. Now, we know that density is equal to mass by volume. So, mass is equal to volume into density. So, here we can write that volume of water divided by into density of water divided by volume of soil, or you can say total volume. If I consider the total volume Vt, then it will be the bulk density of your soil, because bulk density means mass of your soil solid divided by total volume of soil, and here we are considering mass of the soil solid. So, mass of the soil solid is Bd into Vt. So, we are putting this over here, and after that this entire term is that, so theta V into density of water divided by bulk density is equal to theta m, or if you want to find out theta V, it is theta m into Bd by the density of water. So, this is the entire thing how the volumetric water content is related to, yes, void ratio is always greater than porosity, because the volume of the soil solid, it is always less than the total volume of soil. Now comes another thing, that is called water volume ratio or the liquid ratio. So, it is the volume of water divided by the volume of soil solid, because here there is the volume of soil solid, then you will have to assume the particle density, okay. So, it will be gravimetric moisture content into particle density, very important formula. This is also called liquid ratio. Then degree of saturation is how much of your pore spaces are filled with water. So, you will just do the ratio of volume of water present at a particular point of time to the volume of pores. So, volume of water divided by volume of pores, Vw by Vf. And in case of air filled porosity, you will see that what is the volume of air divided by the total porosity. So, these are some of the terms that you should be very okay. Now, another thing I wanted to mention is Okay, so if F is your porosity, suppose, and E is the void ratio, then there is a formula, that is F is equal to E by 1 plus E. This is the formula. F is equal to E by 1 plus E. And then there is another thing, that is, if you have, suppose this is the porosity, if you have this as the air filled porosity, then it is total porosity into 1 minus degree of saturation. So, these 2 or 3 formulas you must remember, so that it will help you with the numericals. Okay. So, with this, with the mass volume relationships, actually we will be ending our soil physics part 1 over here. So, part 2 we will bring, where we will bring about the air and temperature as well as soil water. So, please be with me for the part 2 of the soil physics marathon as well. And if you want to find out the PDFs of all this marathon series, you will find it in the master course or even in the mock test bundle. So, you can just go and subscribe at a very low price it is. So, that's it. Thank you guys. If you are liking our marathons, then increase the participation please, so that you can also know that what are the competing students, okay, who are also preparing for JRF physical science, because social media is a very important platform where you can make all sorts of connections. So, thank you guys, and I want you all to be with me for the soil physics part 2 as well. Okay, goodbye.